So there are two entities on the dark side. One's called dark matter. That makes up 25% of our universe, and it's the kind of the strong gravitational force in our universe. It's the stuff that keeps our own Milky Way galaxy bound together. And the other dark enigma is called dark energy, and this one's really quite mysterious. We've only known about it for the last 20 years or so, and it's this source of energy that appears to be causing the expansion of our universe to get faster and faster each and every day. Now, if you add those up together, dark matter making 70% of our universe, dark matter making 25% of the universe, that leaves us with just 5%, which is the stuff that you and I and the Earth and the Moon and the Sun are made up of. So when I say the dark universe, I mean everything that's not us, that we can't see. Now we know that it's there because of the effect that it has on the things that we can see. I have two different opinions on it. So I'm very proud of the fact that scientists now know exactly how much dark matter there is in the universe and how much dark energy is. That's an amazing achievement that's only come about really in the last few years, to really precise measurements. So that I feel very proud of. But then I'm also a little bit embarrassed because we can't explain dark matter and dark energy. We simply can't explain the two of them. We haven't found a dark matter particle and we don't know the origin of this dark energy source. And that's kind of a bit of a failing for us as scientists to not be able to explain 95% of our universe. So a mixture of feeling proud, embarrassed, and at the same time excited, because when you don't understand something, that means that you can really push forward science. When something's not understood, it means surely must mean a major breakthrough's around the corner to understand this massive dark universe that's out there that we can't see. So at the moment, we're very much in the development phase of what techniques can we use to really probe the dark side of the universe. It's invisible, we can't see it. So what techniques can we use to actually map out the dark matter in our universe and look at how dark energy is changing things over cosmic time? And we're doing really very well with those different probes. Now, in order to explain the dark side of the universe, some of the theories out there are really quite radical, quite far-reaching. So any scientific experiment we make, we're going to need to validate it with lots of different independent experiments, because if the end of this, if our conclusion of this work is that perhaps Einstein's theory of general relativity is missing something, now that's quite radical. So we need to be absolutely sure about our measurements. So we're developing lots of different techniques that we can use to probe the dark universe, using lots of different types of technology. Now you asked me if I could wager a date of when we'll know this. I think our best guess is going to come in the next decade. So in the next few years, we're going to see the launch of the Euclid satellite, which is a major European project that's going to go above the atmosphere, and it's going to give us the most exquisite view of the universe, the entire night sky. At the same time, on the ground, we've got the Large Survey Synoptic Telescope that's going to also be imaging the night sky for 10 years, building up the deepest image that we've ever seen of the universe. And we also have a project called DESI, which is going to be mapping out all of the galaxies in the universe and how fast they're moving. Now, the combination of these three data sets is going to allow us to directly test gravity. It's also going to allow us to directly test different models of what could be causing this dark energy. And these instrumentation, this technology has been designed to really uncover the origin of dark energy. And so if you want me to wager a bet, I'd say the next 10 to 20 years, I hope that we'll see a major breakthrough in this. I'm working on a project called the Kilodegree Survey, and it's one of these precursor projects that are allowing us to really test out the different methods that we're going to be able to use with these major new pieces of technology that are coming on in the future. Now, the technique that we've been pioneering is called weak gravitational lensing. Now imagine you're the observer and you've got a telescope, and I'm some distant galaxies that are billions of light years away. Now between me and you is a whole load of dark matter, a big structure, a cosmic web of dark matter. And the bright galaxies that we can see are within that cosmic web. Now these clumps of dark matter will be bending space and time. Their gravity will be bending space and time. So when light from me shines from me towards you, the observer, the light's not going to travel in a straight line. It's going to be bent and distorted by the gravity of the dark matter. Now we've imaged about 15 million galaxies, and what we look for is tiny distortions in their shape, and those distortions are being caused by the fact that the light gets bent and curved as it travels from me, the distant galaxies, to you, the observer. And with those measurements we can map out the dark matter between those distant galaxies and you. Now this allows us to test lots of different things. So we can test the theory that dark matter dictates where and when galaxies form, and sure enough, where we see big clumps of dark matter, that's where we see massive numbers of galaxies. But we can also look at how those dark matter structures are evolving. So dark matter is a strong gravitational force, it likes to pull structures together, but dark energy makes it harder for those dark matter structures to form. So dark energy is causing the expansion of the universe to get faster. Distances are growing in the universe, which makes it harder for dark matter structures to form. So with this technique, we can map out how these dark matter structures are growing with time, how they're getting clumpier and clumpier, and that allows us to test what the dark energy is doing. Now we found a bit of a strange result that's very interesting. Because what we're finding is the dark matter that we're mapping out is a lot smoother than we expected. Now, there have been very exquisite measurements of the universe right after the Big Bang by something called the Planck satellite. It's made a major breakthrough in cosmology. It's that measurement that's told us exactly how much dark matter and dark energy there is. And that tells us what the universe looks like right after the Big Bang 13.8 billion years ago. And you can take a theoretical model of how you think dark matter and dark energy evolve and exist in our universe, and then you can predict what the dark matter should look like today from those measurements of the universe right after the Big Bang. And they don't meet. So with our theory and our measurements of the universe right after the Big Bang, you'd predict that the dark matter we see today should be a lot clumpier. And the fact that it's smoother than we expect could indicate that dark energy is evolving, that there's something strange happening with dark energy today. Or it could mean that we haven't quite got our measurements right. You know, we're still in the precursor phase, we're still learning how to do these measurements. I think we've done it right, I'm sure the Planck people have done it right, so this could be something really new and exciting, but we need more data, more experiments, more stress testing of the information before we can say something really concrete. In our current theoretical knowledge, we have 4 fundamental forces that explains how we view the world around us. We have our standard model of particle physics that can explain the particles that you and I are made up of. That's our basis, our fundamental knowledge of physics. Now, if we restrict ourselves to that, there's nothing in there that can explain the dark matter particle, there's nothing in there that can explain the origin of dark energy. So we have to go beyond our current fundamental understanding of physics. Now, which way do you go? You can build on those theories, so people are starting to ask questions of maybe we need to go beyond Einstein's theory of gravity. Perhaps we need to extend Einstein's theory of general relativity. Could it be that there are extra dimensions out there? You know, we're used to our dimensions of space and time. Perhaps there's a 5th dimension out there that is somehow influencing our dimension. Maybe there's more than just the 4 fundamental forces. Maybe there's some additional energy force field out there that's causing this accelerated expansion. All of these different ideas are going well beyond our current understanding of physics. And our job, my job as an astronomer, is to build the data sets that we can confront all of these different theories. We're never going to be able to prove a theory, but we can disprove theories by prodding and testing them in lots of different ways with lots of different experiments, and that's our job right now. I believe that there's going to be a major breakthrough just because this question is so large. It's not like there's just a small part of the universe we don't understand. It's 95% of it. You know, it's huge. And the fact that we have these 2 different components, neither of which we really understand. And some theorists are going so far as to say, can I explain these 2 dark entities with the same theory? Perhaps there's some interacting model that can explain both of these dark entities, and that would be fun to understand both in just one foul swoop. But our job at the moment is to build the data sets to test those theories. Most astronomers believe that it's just that we can just look at our universe and understand that there's large regions of our universe which are just filled by a vacuum. And quantum physics would tell us that a vacuum has some energy. It's really strange to think about that a vacuum which has absolutely nothing in it could source energy. But if you have lots of vacuum space, there are opportunities for virtual particles to pop into existence. And this is a theory that comes from quantum physics that have been tested in the lab. It's a really simple explanation for what we're seeing, but the numbers just don't stack up. If you estimate how much energy this effect would give, our universe simply wouldn't exist anymore. It would have been accelerated and expanded away a long time ago. But that's the theory that most astronomers think is the right theory. So if you were really asking me to put a bet on something, then I'd probably go with that. But it's quite boring. And it's much more fun to think that maybe we'll make some major breakthrough in our understanding of gravity. I mean, it is fun to think, today I might prove Einstein wrong. When I was doing my undergraduate degree, it was a very special time because it was when dark energy was first discovered. So I was an undergraduate student at the time. We went along to a lecture. They cancelled the lecture because this amazing new paper had come out that was the first time that the rapid increasing expansion of our universe has been measured using very distant supernovae. And it was that really captured my imagination. And this was in 1998 that this first, it was completely unexpected. No one had foreseen or no observers had foreseen this had happened. Theorists had always predicted that this would be the case, but the observers never thought this would happen. And this first direct evidence of this accelerating expansion of the universe. And that just, I just thought right then and there, this is what I'm going to do my PhD on. I didn't think it would take quite this long to even be starting to approach the answer. I mean, we're still 10, 20 years on before we have the data to really be able to say something concrete about the origin of this dark energy. But it's there. I won't retire until I understand this. Humans, civilization has always wanted to explore. I mean, look way back in history, Columbus exploring, and finding America. It's part of being a human that we want to explore. We've explored the Earth now, we've explored the solar system. I mean, it's amazing that we've sent manned probes past each and every planet in our own solar system and have imaged them. It's an amazing exploration. And I think, as humans, we want to explore. And what better place to explore than the gigantic universe all around us? I think that's a really important question, and I think the answer to it lies in the fact that science and scientists will hold the answer to those terrestrial problems. Climate change is a really important problem that as a civilization we have to face, and whilst it's not my research area, what I do really gets people excited about science. It gets people into science, encourages them to take science at school and at undergraduate level, and it's those people who are then going to go on and solve these important problems. There's another side of things as well is that astronomers actually drive a lot of technology. Take your mobile phone, for example, the digital camera in that. It was astronomers that drove that technology forward, that innovation. Wi-Fi is another example. It was radio astronomers who worked out how to use Wi-Fi and now that's an everyday part of people's lives. So I feel my work's twofold. I get people excited about science, they come in and they learn, and also our science questions are driving technology and innovation to the max.